In this video, we are going to look into mass spectrometry. Mass spectrometry is a method for identification and characterization of organic compounds. It is based on the interaction of organic molecules with high-energy electrons. High-energy electrons are generated, and as they collide with an organic molecule, they eject another electron from that molecule. The result is that as organic molecule loses its own electron, it generates a radical cation. So no bonds are broken, but one of the electrons is ejected, and if it's electron from a bond, then that bond becomes one electron bond, much weaker bond. But no bonds are broken in the course of this process. Energy that is required for an electron to have so that it can eject another electron from a molecule upon collision is about 10 to 12 electron volts. But in practice, electrons are accelerated to about 70 electron volts, so they have much higher energy than needed to eject an electron. That impacts considerably more energy to the molecule upon collision. And as a result of gaining so much energy, then resulting radical cation undergoes fragmentation. And that fragmentation process is very important because it helps us with identification and characterization of organic molecules. Here is a schematic representation of mass spectrometer. A sample organic compound that we want to analyze is dissolved in suitable solvent and injected into the ionizing chamber. Ionizing chamber is exposed to a beam of high-energy electrons. Ionizing chamber is also under vacuum, which causes sample to vaporize, and vaporized sample is then, upon collision with high-energy electrons, ionized. As already mentioned, sample is under vacuum, so vacuum actually draws out all of the particles that are not used in analysis, that are not useful for the analysis. Any neutral or negatively charged particles are drawn out by vacuum pump and expelled out of the instrument. At the same time, positively charged radical cations are accelerated by electrical potential and end up in the magnetic field. So they are deflected in the magnetic field, and they are deflected. The magnitude of deflection depends on the mass of each particle. So light ions are deflected by greatest amount in that magnetic field, while heavy ions are deflected the least. Ions then hit collector, where each hit is recorded. So collector records each hit and sends that information to appropriate recording device, a computer, which then plots the outcome as a histogram, as the abundance, amount of hits at each molecular mass. Electron source in mass spectrometer is a heated electric filament. This is an electric filament similar to ones we have had in old incandescent light bulbs. So when current is passed through such electric filament, due to resistance to passing electricity, filament heats up and electrons leave surface of the metal. Filament becomes incandescent, electrons leave surface of the metal, as I already mentioned, and then when magnetic field is applied, those electrons are accelerated in the magnetic field. That gives electrons high energy, and those are the high energy electrons that collide with organic molecules to ionize them. Here is a schematic representation of an ionizing chamber. First, here in the corner, you have schematic representation of a mass spectrometer, so you can see where ionizing chamber is. And here is the enlarged schematic representation. So ionizing chamber contains setup for generation of high energy electrons that we have just examined. And in the ionizing chamber, our sample is vaporized. Upon injection, because ionizing chamber is under vacuum, the sample immediately vaporizes. Upon collision with high energy electrons, molecules of the sample are converted into cation radicals. There are electric plates at high voltage that are present on the outside of the ionizing chamber. Positively charged plate, of course, repels cations, and it's called ion repeller, so it repels cations away from itself, while focusing lenses are negatively charged and attract ions towards themselves. They have a hole, and so as ions or radical cations are attracted towards focusing lenses, they pass through the hole and enter the mass spectrometer. So they enter the magnetic field where they are deflected. This is actually a schematic representation of an older instrument, because these days we usually don't use magnets. We use what is called TOF, time of flight instruments, where time of flight of individual ions is measured. Such instruments are much less expensive and they are much smaller compared to older magnet-based mass spectrometers. Common mass spectrometers are what we call low-resolution mass spectrometers. A low-resolution mass spectrometer has accuracy of plus or minus 0.2 atomic mass units. That's actually good enough for most purposes. For example, if we find that a molecule has a molecular mass of, let's say, 44, that means 44 plus minus 0.2. Well, that means it's exactly 44, it's not 43 or 45. And that's good enough for most purposes. Much more accurate instrument, much more sensitive instrument is high-resolution mass spectrometer, and that one has accuracy of 0.0001 atomic mass unit. Obviously much higher accuracy, and much higher accuracy, of course, comes at much higher cost. That's not needed for most purposes, but actually it does become occasionally very important, because such high accuracy could allow us to determine molecular formula of a molecule, if it's molecular ion, or molecular formula of the fragment, if it's fragment in question. That's because mass spectrometer, of course, identifies particular isotopes, and masses of isotopes are frequently known to a fourth decimal place. So as a particular mass is determined by the instrument, only certain combination of isotopes of elements will give that particular specific mass. And here is an example. Both carbon dioxide and propane have molecular mass of 44. And so low-resolution mass spectrometer for each of these molecules would give mass as 44. But carbon dioxide is composed of one carbon and two oxygen molecules. And the most common isotopes of carbon, 12, and oxygen, 16, give molar mass of 43.9898 atomic mass units. While propane has 3 atoms of carbon and 8 atoms of hydrogen. And so combination of the most abundant isotopes of carbon-12 and hydrogen-protium gives molecular mass of 44.0626 atomic mass units. And while low-resolution mass spectrometer cannot distinguish between the two, high-resolution easily distinguishes between the two. And in fact, usually there are computer programs that as soon as the value is obtained, programs will match it with a particular combination of atoms and then actually print a molecular formula for that fragment or a molecule. Most common applications of mass spectrometry are to determine molar mass of a compound. So if compound is unknown, we can determine its molar mass. To identify a compound, mass spectrum is actually a fingerprint of a compound. Each compound has a unique mass spectrum. So unknown sample could be compared with library of known spectra, and if there is a match, then compound could be identified. And these days, computer programs do that comparison and actually can print how a good match is. And finally, mass spectrometry in some instances can be used to establish a structure of an unknown compound. An important feature of mass spectrometry as a method is that radical cation is unstable and undergoes fragmentation. That fragmentation is predictable, so it follows predictable pattern. common stable daughter ions, they're called daughter ions, are generated. And so here are some of the most common ions. I will not go over them. If you wish, you can pause the video here and examine them in more detail. But you can see that molar mass, or actually mass, not molar mass, but fragment mass is easily determined. So for example, 15 corresponds to methyl group. 1 carbon and 3 hydrogens, that's 15, so that's methyl group. 18 would be water, and so on. 44, loss of carbon dioxide. 45, carboxyl group, and so on. So these fragments can be easily identified, and then, like a jigsaw puzzle, we may be able to put together those fragments to figure out structural formula of a molecule. Usually, we combine this information with other spectral information to determine structural formula of a molecule. Since mass spectrometer identifies fragments of particular masses, it means that it identifies fragments that contain particular combination of isotopes. Mass spectrum is a histogram, and soon you will see some examples of mass spectra. And that means that it plots or prints relative abundance of each of the fragments. In turn, that also means that if there are fragments that contain different isotopes, then histogram will show relative abundance of each of the isotopes. I will not go over each of these isotopes in the table. Again, you can pause the video here if you wish to examine the table in more detail. But for example, you can see that fragment that contains carbon-12 will be present in natural abundance of about 99%, 98.9, and carbon-13, 1%. So, particular fragment, let's say a methyl group that may appear in the mass spectrum, will actually show two signals in a ratio of 99 to 1 that reflect natural abundance of isotopes carbon-12 and carbon-13. Now, that may be sometimes useful to infer or even positively identify presence of certain elements in a molecule. That's frequently the case with halogens like chlorine and bromine. Chlorine is naturally present or naturally occurs in form of two isotopes, chlorine-35 and chlorine-37. So it's going to give two signals in mass spectrum. Signal for chlorine-35, and we would label that as M, and 37 M plus 2. Chlorine-35 has natural abundance of about 76% and 37 24%. Approximately, they will be present in 3 to 1 ratio. So if we see in a mass spectrum signal M that has intensity of about 3 or height of about 3, and then M plus 2, 1, so M and M plus 2 have ratios of 3 to 1, then we can infer presence of chlorine in that molecule. And sometimes we can even see a pattern that would show us presence of two chlorines in a molecule. Similarly, in case of bromine, there are two isotopes, bromine-79 and bromine-81, that are naturally occurring in about 1 to 1 ratio. So presence of M and M plus 2 signals, M and M plus 2 ions, in approximately 1 to 1 ratio would indicate presence of bromine. And you can see presence of those signals M, M plus 2, and M plus 4 in approximately 1 to 2 to 1 ratio would indicate presence of two bromines. Now we are going to look at a couple of examples of mass spectra. First, here is mass spectrum of toluene. We start any analysis of a mass spectrum at highest masses. First, we try to identify molecular ion, M+. That one tells us molecular mass of a compound. So here we look at, first this is fragmentation pattern, we'll look at that later, but we look at highest masses. So we can see that there is a cluster that is 91, 92, 93. Most organic compounds have even molecular mass. So in this case, we should assume that molecular mass is 92, that molecular ion M plus is 92. Unless molecule contains odd number of nitrogens, molecular mass should be even. Only molecules that have odd number of nitrogens have odd molecular masses. And since here we don't have an indication that molecule contains nitrogen, then we'll assume that 92 is M+ ion. There is small signal at 93, that's M + 1. That's due to presence of carbon-13 isotope. So naturally occurring carbon has 1% of carbon-13, so M + 1 and sometimes even M + 2 signals are visible. M + 2, of course, would be due to presence of 2 carbon-13 atoms in particular molecule. We can see that the most abundant peak in the spectrum is base peak. So besides molecular ion, so that's one important peak in the spectrum, molecular ion. Second peak that is important is base peak. Base peak is the most abundant peak in the spectrum. In this case, it's 91. It's a result of loss of proton, H+. Sometimes when mass spectrum is reported in literature, in print, base peak is assigned abundance of 100, and that's shown on the left as relative intensity, and all other peaks are reported as percent intensity relative to base peak. So we can explain M+ ion as molecular radical cation generated as a result of electron impact, and then 91 peak as a result of loss of hydrogen. That 91 is actually tropylium cation. It's benzylic cation, but under these conditions in gas phase, it rearranges into more stable aromatic tropylium cation. Then loss of a fragment, 26, that's molecule of acetylene, very stable molecule, acetylene or ethyne, results in formation of this cyclopentadienyl cation at 65. Cyclopentadienyl cation itself is not very stable and loses another molecule of acetylene to give this cyclopropene cation with a fragment 39. So this is how we analyze a mass spectrum. We start at molecular ion and look at what are the fragments that are lost. It would be wrong to start at small molecular masses and attempt to identify fragments by looking at those small fragments, because those could be contamination or something from the air. Instead, we should always look at fragments that are lost from the molecular ion and from the resulting fragments. Also note that we are looking only to identify the most important fragments and what structural information they give us. We don't have to identify every single peak, and in fact most of the time we don't. We don't have to identify what every single peak in mass spectrum is due to. A lot of them are actually not important. Now we are going to examine mass spectrum of benzaldehyde, and again here is the fragmentation pattern associated with it. Again, we start at highest masses, and now we can identify molecular ion at 106. In this case, molecular ion overlaps with base peak. Again, we can see M + 1, and if you have good eyesight, you may even be able to see small peak due to M + 2 ions. Now, besides molecular ion at 106, we can also identify 105 ion, very prominent peak. That's again due to a loss of hydrogen atom. So this is acylium cation, very stable cation, and that's why peak is so strong. Next, there is a loss of fragment 28, that's carbon monoxide, and that gives fragment 77, very characteristic fragment. And not only 77, but we can see a cluster there. Cluster that appears there at 76, 77, 78 is an indication that benzene ring is present in the molecule. This cluster could be of different intensities, but whenever you see that cluster, you should always suspect that benzene ring is present in the molecule. And fragment 28 is characteristic fragment, that's carbon monoxide. It could also be ethene, C2H2. And then next, we have loss again of acetylene, 26, and this gives cyclobutadiene cation at 51. And that's pretty much all the information we can get from mass spectrum of benzaldehyde. This completes our study of mass spectrometry, and next we are going to look at ultraviolet visible or UV-vis spectroscopy.